All right, so today we're going to be talking about complex power. Complex power is a quantity used by power engineers to succinctly characterize the power absorbed by a given load in a sinusoidal steady-state circuit. It is a powerful quantity in steady-state sinusoidal power analysis because it contains all of the information pertaining to the power absorbed by a given load. So let's consider a generic impedance, Z, like so, across which some phasor voltage V occurs and some phasor current I flows through. Now we know that our phasor voltage V will be of the generic form Vm angle theta V, and our phasor current I will be of the generic form Im angle theta I. These are our frequency domain relationships. Well, complex power is typically worked with in a slightly different perspective. So we can transform these frequency domain relationships to what are called RMS phasor domain relationships, or at least that's what I call them. When we're working in the RMS phasor domain, our phasors are represented with a tilde over the capital letter as opposed to just the bar. And we convert by simply dividing our phasor voltage by the square root of 2, which means all we're really doing is using the effective values that we discussed in the last class. This would be VRMS with an angle of theta V, and similarly our RMS phasor current would be our phasor current divided by the square root of 2, giving us I RMS angle theta I. So complex power is defined as S, which is going to be our symbolic representation of complex power, is 1/2 our phasor voltage times the conjugate of our phasor current in the frequency domain. And obviously then this would simply be equal to RMS phasor voltage V times the complex conjugate of the RMS phasor current I, like so. So this is the RMS domain. Since complex power is the product of a phasor voltage and a phasor current, it may seem that the fundamental unit of complex power should be the watt. But in practice, power system engineers use the unit volt ampere, so VA, to quantify complex power. And this is done to avoid confusion with the average power, which is measured in watts. You look confused.
I just don't understand the complex power.
So complex power is a shorthand notation that electrical engineers have created to avoid having to do and carry around a bunch of really unimportant pieces of information regarding the power absorbed by a particular load. So up to this point, we've been dealing a lot with instantaneous power, right? Well, the instantaneous power is by definition an oscillatory power meaning that it's going to oscillate between its maximum positive value and its maximum negative, and it's going to have some average value over time in any steady state sinusoidal circuit. So all this complex power is doing is just another way of looking at that, where we're saying the fluctuations don't really matter. We're mainly concerned about the average, or how this thing behaves at steady state. And we are going to relate this quantity, complex power, specifically to the average power that we computed before, which was a portion of the instantaneous power, right? It was the DC portion of the instantaneous power, but we're also going to relate it to specific design criteria that is required by power systems engineers to be able to safely distribute power.
So what is the imaginary part? I'm very good.
Yeah, we'll be getting to that in a second. So yeah, so, okay, yeah, so we'll talk quite a bit about reactive power in a couple minutes. All right, so complex power is RMS phasor voltage times RMS phasor current. Conjugate has units of volt amperes. So if we substitute in okay, so it's obviously a complex number, right? So we can actually use Euler's identity to express it in a couple of different ways. Okay, so we could say that our complex power is going to be, so if I'm using Euler's identity, I'm going to have the magnitude of my voltage, so that would be V RMS times the magnitude of my current, I RMS, times the cosine of theta V minus theta I, plus J VRMS IRMS sine theta V minus theta I. And I can express that complex number as a polar form complex number as well, just by simply multiplying my RMS phasor voltage and my RMS, the conjugate of my RMS phasor current, which would give me simply VRMS IRMS with an angle theta V minus theta I. So let's look particularly at the real portion, okay? So the real portion of our complex current, or excuse me, complex power S is VRMS IRMS cosine theta V minus theta I. We can break this down a little bit, recognizing that VRMS is simply Vm divided by the square root of 2, and IRMS is simply Im divided by the square root of 2 cosine theta V minus theta I. And those two factors of 1 over the square root of 2 multiplied by each other give us 1/2 Vm Im cosine theta V minus theta I. So we can see that the real part of our complex power S is the exact same average power that we derived from our instantaneous power relationships, okay? The average power represents the portion of the complex power that can perform work at the load and is measured in watts. Okay, so we've talked quite a bit about average power to this point. We're just looking at it from a slightly different perspective, or actually, we're not even looking at the average power from a different perspective. We're looking at calculating it from a slightly different perspective, right? but it is the exact same thing that we have talked about before. So now let's look at the imaginary portion of S. So the imaginary portion, VRMS, IRMS, sine theta V minus theta I is more commonly referred to as Q, the reactive power. Reactive power is measured in volt amperes reactive, okay? So the reactive power represents the portion of the complex power that continuously flows back and forth between the source and the load in the system. So it's representing what's happening, or the contribution of inductors and capacitors in the system, because we know that for a capacitor and for an inductor, exactly half of the time the element is absorbing power and exactly half of the time the element is supplying power. So the complex power represents that contribution. A pretty common question that you might get asked is, well, why does complex power matter? So capacitors and inductors are forms of temporary energy storage in an electrical system, okay? So complex power, the ability to either quickly inject it into a system or take it out of a system, is used in a lot of power distribution systems where we have irregular loads. So take into account like something like the Super Bowl, right? Here in the United States, for when the Super Bowl is on TV, there is a significantly increased demand on the power infrastructure that isn't there at other times. To avoid blackouts and things like that, reactive power is injected into the system by connecting temporary energy storage in the form of capacitor banks and things like that to help smooth out that load so that the demand doesn't cause the voltage drop to go down so much that we observe brownouts and blackouts. So that's what reactive power is all about. It's temporary energy storage for a large scale distribution system. Reactive power is also responsible for maintaining the magnetic flux, which keeps an electric motor spinning. So that's the other huge application of reactive power. Without the presence of those inductors and capacitors that are creating the reactive power in our system, industry wouldn't work and we would have blackouts fairly regularly.
So as far as they get used, if you only had a resistor, you have zero reactive power, right?
That's correct.
And you said that reactive power is when it describes how capacitor and inductor half of the time it's supplying power and absorbing power.
Mm-hmm.
So when it's absorbing power, wouldn't that be part of the real power?
No.
It's all still reactive?
Yes. So just because it's absorbed doesn't mean it's capable of doing work. All it's doing effectively is creating an artificial maximum for the amount of current that can be supplied. So when we talk about power factor in 7 or 8 minutes or whatever, maybe that'll help things out as well there, because power factor is all about the efficiency of a system, meaning how much power you're generating that can do work to the how much power you're generating in total. So kind of jumping ahead a little bit, if you have a load that is drawing reactive power, that means that the power company has to be able to supply a certain amount of power, even though some portion of that is immediately going to get sent back to them. They still have to burn the coal or utilize the turbines or whatever. It costs them money in infrastructure, headroom and stuff like that, to be able to generate that power, even though that power isn't consumed by the end user because it isn't capable of doing mechanical work. Does that make sense?
Yeah.
Yeah.
So there's another question again. If a motor is an inductor, right?
It has inductance and resistance.
Yeah, that's all my question. How does it consume power with an inductor?
Yeah, so it's not just, and most motors are more resistive than they are inductive. And if you think about it, it's because, so yeah, there's a lot of coils generating inductance for sure, but those coils are made out of wire, and real wire has resistance. All right. If we look at the magnitude of S, this is simply VRMS times IRMS, commonly known as S with no bar or anything like that over it. This is what's called the apparent power. Apparent power is measured in volt amperes, and this is the typical design constraint for a system, because this really represents the maximum amount of average, so I hate to say the maximum amount of average power because that's not really true. It's also not the maximum amount of instantaneous power, but it's kind of like the maximum amount of steady state power that you could possibly ever need. And the reason I say that is because it doesn't take into account the phase angles at all. So it doesn't take into account effectively constructive and destructive interference. It's simply the product of the magnitude of the voltage and the magnitude of the current. So this is kind of like worst case scenario, somehow you might have to supply this amount of power to a system. So just to be clear here, we have average power measured in watts, symbolized by P. Sometimes I'll write P average, other times I'll just write P. Then we have reactive power, symbolized by Q, measured in volt amperes reactive. And then we have apparent power, symbolized by S and measured in volt amperes. Bless you. So the last part of our complex power relationships is the argument of our complex power, which is theta V minus theta I, or we might call it theta S, and this is what's called the power factor angle. All right. So since theta S, or the difference in those phase angles, is called the power factor angle, it probably makes sense to go into some detail about what the power factor is. So the power factor at which an electrical element or network operates is a measure of the efficiency of power transmission to or from the network. Mathematically, power factor is defined as the ratio of the average power compared to the apparent power, or simply as cosine theta V minus theta I, which is identical to cosine theta S. So since the cosine function, by definition, ranges from +1 to -1, the value is then a measure of the efficiency. So if the power factor is exactly 1, that means that the load is absorbing apparent power with 100% efficiency, meaning that all of the apparent power, or the value of the apparent power and the value of the real power or average power are the exact same thing. So that would be exactly what's true for a resistor. If the power factor were -1, then that means that our load is supplying power at 100% efficiency, right? Now, if the power factor is 0, which would be the case for any load that is purely capacitive or purely inductive, then that means that we are operating at 0% efficiency, which means we have no average power being consumed by the load. Okay. So power factors are classified as leading or lagging depending on the sign of the power factor angle. So when 0 degrees is less than theta s is less than 180 degrees, our power factor is considered lagging. So what this means is that the current lags voltage. When -180 degrees is less than theta s is less than 0 degrees, we have a leading system. Where the current leads the voltage. So for a lagging system, typically speaking, and I say typically, but it means 100% of the time, it can't not be that. We have an inductive system, meaning that the overall impedance of our system, it may be purely inductive. More than likely it has some resistance. It does not matter whether that resistance is positive or negative. So you may be saying, well, what the heck is a negative resistance? These fluorescent lights are negative resistance, actually. It's something to do with the way that the ballast operates. I don't know enough about it to explain it better than that, but fluorescent lights, because they work by ionizing a plasma in these tubes, winds up behaving as if it were a negative resistance. And when the current leads the voltage, we have an overall capacitive system. Okay. When our power factor is exactly +1, -1, or 0, we don't consider those to be leading or lagging, right? So a power factor of unity or 1, the voltage and current don't lag each other, don't lead or lag each other, because it turns out they have to have the exact same phase angle. For a power factor of -1, they're not neither leading or lagging because they are exactly 180 degrees out of phase. And for a power factor of 0, they're neither leading or lagging because they're exactly 90 degrees out of phase. So if they're pi/2 or pi away from each other, or 90, or some integer multiple of 90 degrees away from each other, we can't tell which one is leading and which one is lagging. All right. Typically speaking, loads operating below a specific power factor threshold So that might be something like a 95% or 97.5%, incur fines from the utility company supplying it to offset the increase in transmission costs. So what that really means is a power utility company really supplies only apparent power. Okay, from its perspective, it supplies apparent power, but it charges its consumers for average power. That's what the watt meters and all that kind of stuff attached to the side of your home measure, the amount of average power that you are consuming, right? So they fine you if your power factor is too low because they're spending money to generate apparent power, but you aren't paying for it, okay? So they'll fine you for the increased costs in the infrastructure necessary to do that. So that cost may come in having to use larger wires to send the increased amount of current. So if you think about the utility distribution company, they're providing a specific voltage to your home, residence, business, whatever you want to call it. Their job is to supply pretty much 120 volts RMS to every receptacle in your home. If your loads are drawing too much reactive power, then in order to keep that voltage at that level, they have to be supplying reactive power to you. But that reactive power doesn't get used, doesn't show up on a watt meter or anything like that, because it gets sent to you and then immediately gets sent back. So even though they paid money ostensibly to create it, they can't charge you money for it because it was never used. So they fine you as a way to make you pay for it.
How do you figure that out?
So they simply look at the ratio of what they're making versus what you're using. I mean, it's literally that. Yeah. All right. So I'd like to talk about the power triangle next. So to help facilitate an easier understanding of the power relationships for a given load, power engineers have developed a graphical tool which illustrates these relationships in the power triangle. So let's consider a generic inductive load. So our load, that line is not remotely straight, will have some positive resistance and some positive reactance, like so. Our horizontal axis is the real axis. Our vertical axis is the imaginary axis. And let's say that the complex power absorbed by our load is S. Well, the projection of S onto the real axis is the average power. The projection of S onto the imaginary axis is the reactive power. The magnitude of S is the apparent power. And the angle formed between our complex power S and the horizontal axis is our power factor angle, theta S. So from this triangle, we can easily see that S is VI conjugate, and in rectangular form, we have P plus JQ. And in polar form, we have S angle theta S. One thing that's interesting and can be of considerable use depending on the type of questions you're asked is that the power factor angle theta s is determined purely by the impedance of the load, because theta s by definition is theta v minus theta I. Theta v minus theta I is also the angle of the impedance in polar form. So they represent the exact same quantity. So when we look or develop a power triangle like this, we can actually tell an awful lot about it. So if the triangle exists in the first quadrant, like the one that I've drawn here, then our load is obviously inductive. And so our power factor should be between 0 and 1, and it should be lagging. If our power triangle wound up being in quadrant 4, that would mean that our load is capacitive because our phase angle is negative. We would know that it's absorbing because the real portion is positive while the imaginary portion is negative. There's a ton of information that can be gleaned just by a quick glance at these power triangles. So what I typically tell, doesn't matter if they're circuits 1 students, circuits 2 students, whatever. At this point, once we've introduced the concept of effective values, it does not matter what power quantity I ask you for, other than instantaneous power. You should just calculate the complex power and then use that to get your other quantities, because they're all built in to this one little thing. And especially nowadays that you guys have relatively inexpensive calculators that can present you the complex power in either polar form, which gives you immediate access to apparent power and the power factor angle, or rectangular form, giving you immediate access to average power and reactive power. There's really no reason to memorize those 10 equations I gave you earlier if you can understand those two simple relationships and use your calculator effectively. The only thing that you need to memorize is V times I conjugate and the triangle. And you have everything built into those relationships. So one of the last things that I want to talk about before we get into some example problems here are alternative relationships. And so these are the relationships that I derived in instances where I didn't want to have to know both the RMS phasor voltage and the RMS phasor current. So if it's easier to just calculate the voltage, then we can use one relationship. If it's easier to just calculate the current, we can use the other, instead of having to fall back on always needing to know both quantities. Because sometimes it'll be much more easy to calculate one than the other. All right, so all of these simply utilize Ohm's law in the RMS phasor domain. So to be clear, what I'm talking about is V RMS phasor is equal to I RMS phasor times Z, which is the exact same relationship in the frequency domain and the exact same relationship in the time domain. Ohm's law is always V is equal to I times R. It's pretty great. So if our complex power S is V times I conjugate, we can substitute in I times Z times I conjugate. Do any of you guys recall what happens when you multiply a complex number by its conjugate? So you guys are kind of close-ish, but not kind of spot on. So I'm going to do it down here real quick. So let's say that we have a complex number A that is A plus JB, or the magnitude of A with an angle of theta A, right? So that means that A conjugate would be either A minus JB or the magnitude of A with an angle of negative theta A, right? So if I multiply A times A conjugate, that's going to look like the magnitude of A angle theta A times the magnitude of A angle negative theta A, which is just the magnitude of A squared. If we did it in rectangular form, it would just be A squared plus B squared, which is still the magnitude of A squared. So when I multiply my phasor current, my RMS phasor current times its complex conjugate, all I'm left with here is IRMS squared, the magnitude squared, multiplied by my impedance Z, which in polar form is going to look like IRMS squared times the magnitude of the impedance with a phase angle of the impedance. And in rectangular form, that will be IRMS squared R plus J IRMS squared X, where explicitly here I'm stating the impedance is the magnitude of Z angle theta Z. Oops. And here I'm saying Z is expressed as R plus AX. So polar form and rectangular form. If we use the alternative relationship, where I is V over Z, we have to conjugate the whole thing. So I'm obviously going to have V times V conjugate, which is going to be simply VRMS squared. But now I'm going to have to divide by the conjugate. When I take the conjugate of that fraction, I'm conjugating the numerator and I'm conjugating the denominator. So this is going to look like VRMS squared over the magnitude of Z with an angle positive theta Z, or in rectangular form, VRMS squared over the magnitude of Z squared times R plus J VRMS squared over the magnitude of Z squared times X. Again, using the polar and rectangular form of the impedance. So now, for a purely resistive load, meaning R, I'm going to say that it's greater than 0, but it doesn't actually have to be greater than 0. We just haven't used negative resistances to this point. And X is exactly equal to 0. Complex power absorbed by a resistor is simply IRMS squared times R, or VRMS squared over R. So this looks exactly like our simple DC relationships that we learned the second or third day of Circuits 1. Once we learned Ohm's law, we get to use that exact same thing, and it represents a complex power. So that's another added benefit of using RMS phasors, is that I don't know if you guys noticed, but there is a common factor of 1/2 that showed up in everything. And it's from that trig identity, where when we multiply cosine angle 1 times cosine angle 2, it's 1/2 cosine the difference of the angles plus 1/2 cosine the sum of the angles. Using effective values gets rid of all those spurious 1/2s, makes it the analysis look much more like a DC circuit. For a purely inductive load, where R is equal to 0 and X by definition will be greater than 0, we'll see that we have the complex power is equal to J omega L times I RMS squared, which is J times V RMS squared over omega L. So this is an interesting result because it does not matter the magnitude of the voltage or the magnitude of the current. We will see that inductors always absorb reactive power. And this thing down here. For a purely capacitive load, where R is equal to 0 and X is negative, we have SC will be equal to negative J I RMS squared over omega C is equal to negative J omega C V RMS squared. So capacitors always supply reactive power. All right, so we have 30 minutes remaining in class. So we have two options to talk about. We can either work some example problems using these relationships, or we can cover power factor correction and then spend all of tomorrow's class doing example problems over the whole thing. Which would you prefer?
I like,
Doing all example problems tomorrow? Okay. All right, so let's talk then about power factor correction. So let's say that we have a load whose power triangle looks like this. And I'm going to call this S old, so that the projection of S old onto the real axis is P old. The projection of S old onto the imaginary axis is Q old. And we have some angle here, which I'm going to call theta S old. All right. So if this load is operating at too low of a power factor, in order to increase our power factor to an acceptable level, we have to change the value of this angle, theta S old, right? So if we want to increase the power factor, do we need to make that angle larger or smaller? Right, so it needs to be smaller because by definition, power factor is cosine theta V minus theta I, or cosine theta S. So if we want the power factor to increase, we want the angle theta S to be closer and closer to 0, right? Because cosine of 0 is 1, and then it decreases as the angle gets larger and larger. All right, so we need to decrease this angle. We can do it in one of two ways. The first way that I'm going to discuss mathematically works, but it's about the dumbest possible way that you could do it, okay? So I'll do it in red. So let's say that we were trying to correct the power factor by increasing the resistive portion of our load, meaning that we would have some P nu here, and then we would obviously have some angle theta nu, which will be smaller, so that our power factor is increased. The problem with this is not mathematical. Mathematically, it works beautifully. The problem is that in practice, if we lower the power factor in this way by increasing the average power consumed by our load, we are paying a higher utility bill to avoid paying a fine, which makes absolutely no sense whatsoever, right? So mathematically, it absolutely works. In practice, it's absurdly stupid. Okay. So our other option would be to try to decrease the amount of reactive power that is consumed by our load. So if instead we held the average power constant so this will be S nu, and the projection of S nu gives us some new reactive power, Q nu. Our angle, theta S nu, is smaller, right? And we are not increasing our average power consumption, meaning we are not increasing our bill to offset a fine. We are simply lowering, we're raising our power factor by lowering the amount of reactive power absorbed by our system. So how can we accomplish such a feat? Maintaining the exact same, average power while lowering the apparent power absorbed. The capacitor, exactly right, because capacitors supply complex power or they absorb negative complex power, right? So right now, our load is something like this, just for the sake of argument. We have some voltage source and it is supplying some resistance. Doesn't really matter if it's in series or in parallel because they'll both behave like an inductive load. So this is what the old quantity represents. And then what we're doing is we're throwing a capacitor in parallel that will wind up lowering the power factor at which our source is supplying power. So now what we need to do is figure out how to relate our old power factor, our new desired power factor, and the value of C to each other, right? So I can say that S old is P old plus JQ old. And I can say that S new is P old, because we are not trying to change the amount of average power absorbed by our system in any way in the power factor correction process, plus JQ new. So the complex power that must be provided by our capacitance is simply S new minus S old, which will wind up being J Q new minus Q old. Okay. Now, in order to increase our power factor, this quantity must be negative, because we are trying to supply or inject reactive power into the system. Okay. Now, the alternative relationships that we defined just a couple of minutes ago told us that the complex power supplied by a capacitor was negative J omega C times the RMS voltage across the capacitor squared. So if we relate those two different expressions for the complex power supply or absorbed by a capacitor, what we find is that C is equal to negative Q new minus Q old, which is inherently a negative quantity to begin with, divided by omega times V RMS squared. There's also a way to relate it to the average power using tangents, but I can't remember what that relationship is off the top of my head. This is the one that I use 99% of the time. Just a second. Let me think about it for just a second. The reason why that tangent-based relationship is useful is because the tangent-based relationship winds up just using theta new and theta old instead of q new and q old. I want to say that it is P old, which is a constant quantity, tangent of theta s old minus the tangent of theta s new divided by omega VRMS squared. I'm not 100% sure on that, so let me think about this real quick. So P old, so tangent theta s old is the same as sine theta s old over cosine theta s old, where cosine theta s old is my power factor, right? So that would be defined as P over S so S sine, so that is the old, yeah, okay, that works. So it gets rid of the negative sign times the negative quantity and all that kind of stuff and winds up just being the apparent power times the sine of the power factor angle, which is Q. Yeah. And then it's old minus new to get rid of the fact that we have -1 times a negative quantity. All right. Okay. So that is power factor correction and the two different relationships that we can use to solve for the value of C to correct from a old power factor angle, which is below our threshold for being fined, to a target power factor angle. All right. So anything else you guys want to talk about today?